What if I told you that we have a new way to sense the universe? A way that doesn't rely on light, but on something much more fundamental. A way to listen to the very fabric of reality as it stretches and squeezes. This is the story of gravitational waves, the heartbeat of spacetime. And by the end of this video, you'll understand how we are using them to unlock the universe's deepest secrets. Our story begins over 100 years ago, with this man, Albert Einstein.
Imagine space-time as a fabric, and objects with mass warp this fabric.
In 1916, as part of his groundbreaking theory of general relativity, Einstein made a startling prediction. He realized that space and time are not separate things, but are woven together into a four-dimensional fabric called space-time. Think of it like a giant trampoline. Massive objects, like stars and planets, create a deep in this fabric. That's what we feel is gravity. But Einstein went a step further. He said that if you have truly massive objects, like two black holes orbiting each other, they don't just create a deep, they create ripples. These are gravitational waves. They're like the ripples in a pond, when you throw in a stone. From their point of origin, they move outward at the speed of light, carrying information about the catastrophic event that triggered their creation. But there was a catch. Einstein himself believed that these waves would be so incredibly faint by the time they reached us, that we'd never be able to detect them. For almost a century, it seemed he was right. But the physicists didn't give up easily. They came up with a clever and incredibly ambitious idea to detect these waves. It's called LIGO, short for Laser Interferometer Gravitational Wave Observatory. Imagine two 4-kilometer-long tunnels, arranged in an L shape. Inside each tunnel is a near-perfect vacuum. A powerful laser beam is split in two, with one half sent down each arm. These beams bounce off mirrors at the end of the tunnels, and return to the starting point. Now, here's the clever part. The lengths of the arms are so precisely controlled that, when the laser beams recombine, they cancel each other out. So, no light reaches the detector. But, if a gravitational wave passes by, it will stretch one arm of LIGO and squeeze the other, by an amount thousands of times smaller than the nucleus of an atom. This tiny change is enough to knock the laser beams out of sync. They no longer cancel each other out, and a flicker of light appears at the detector. By digitizing and recording these patterns of light, researchers can analyze what they see. They compare the data to computer models of predicted gravitational wave signals. This allows them to identify the source of the waves, whether it's two merging black holes, a pair of colliding neutron stars, or any other cosmic event. The effects of the gravitational waves on the LIGO instrument have been vastly exaggerated in this video, to demonstrate how it works. In reality, the change in the length of LIGO's arms is incredibly small, just 1/1000th the diameter of a proton. The exquisite stability of its mirrors and its advanced technology make LIGO the most precise ruler ever built, capable of measuring the faintest whispers from across the cosmos. On September 14, 2015, after decades of work, it finally happened. A faint chirp was detected at both of LIGO's observatories in the United States. It was the signal from two black holes, 1.3 billion light-years away, each about 30 times the mass of our Sun, spiraling and merging into each other. For the first time, we had heard the sound of the universe's heartbeat. So, what have we learned from listening to the universe? A lot. We've confirmed that black holes are real and that they merge. We've even heard the collision of two neutron stars, which are the incredibly dense remnants of dead stars. This event was particularly special, because it wasn't just heard by LIGO and its European partner, Virgo. It was also seen by telescopes all over the world. This was the birth of a new era in astronomy, the multi-messenger astronomy. It's like watching a movie with both picture and sound for the first time. By combining the information from light and gravitational waves, we were able to confirm that these collisions are where most of the heavy elements in the universe, like gold and platinum, are created. So, the gold in your jewelry was likely forged in the heart of a cosmic collision that we can now listen to. The discoveries didn't stop there. Just recently, scientists announced another incredible breakthrough. They've found evidence for a different kind of gravitational wave, a persistent, low-frequency hum that permeates the entire universe. This is the nanohertz gravitational wave background. So where is this cosmic hum coming from? The prime suspects are supermassive black holes, millions or even billions of times the mass of our Sun, which are found at the centers of most galaxies. As these galaxies merge, their central black holes slowly spiral into each other, creating a constant background of gravitational waves. To detect this, scientists use something called a pulsar timing array. They monitor dozens of pulsars, which are rapidly rotating neutron stars that act like incredibly precise cosmic clocks. The gravitational wave background causes tiny, but detectable changes in the timing of the pulses from these pulsars. It's like we're using the entire galaxy as a giant gravitational wave detector. So what's next? The future of gravitational wave astronomy is incredibly exciting. We are building a global network of detectors, with observatories like Kajra in Japan, and the upcoming LIGO-India, which will help us pinpoint the sources of these waves with even greater accuracy.